Hey students, I got a great question from the harder book, and it has to do again with Lenz's law. And so let's just run through these 6 examples. But right here it says use Lenz's law to determine the direction of the induced current. And so let me just comment on Lenz's law. Lenz's law says that the current will be set up, the induced current. That's what's called induced, because something's changing with the magnetic field. And then what it does is it activates or induces a current in some other circuit. I often call it the secondary circuit. And that secondary current then makes a additional flux, which I often call the secondary flux. So in other words, as the primary flux is changing, it induces some current. That current makes a secondary flux. And the idea of the secondary flux is to keep the total flux unchanged. And so we like to say it opposes the change. And I want to emphasize that because the beginning student often doesn't hear that it opposes the change. What they hear is it opposes the flux. And I want to emphasize it doesn't oppose the flux. It opposes the change in the flux. Another way of saying the same thing is it likes to keep it the same value. Watch. Let's look at A. A here has this metal rod, and as it says, the velocity is moving inward, and the blue dots mean that the magnetic field, the flux from what I'll call the primary, they don't really show where this magnetic field is coming from, but there might be like under the paper a giant magnet, and the magnet has the North Pole pointing up, and so the flux is coming up. Doesn't really matter where we get this primary flux. The point is, as this bar is closing, this right here then is going to create a little loop. And if these are all made out of conducting materials, then a current is going to be established. And the current is going to be established, thereby making another flux, a secondary flux. And that secondary flux is going to be set up in such a way that between the primary and the secondary, it remains unchanged. All right. So watch what happens here. As this bar is moving inward, there is less and less flux coming out. And that means that the current in here, in the secondary, wants to be set up to make up for that deficit. It wants to leave it unchanged. It opposes the change. So sometimes I like to just use the word number 10, and I like to go 10 outward. So before this bar started to move, we had 10 blue dots pointing outward. So clearly, as the bar moves, and in this case, it's moving to the left, the 10 out is going to drop down to, say, 9 out or 8 out. So the current will be set up in such a way to get us back to 10. So if it dropped down to 2 out, the secondary would be created to make 2 out. So we have 8 still left from our primary, and then the 2 created from our new induced current, our secondary, making us back at 10. And so that's why I keep saying it opposes the change. It doesn't oppose the flux itself. If you thought that, you might think, oh, the flux got to go inward because this flux is outward. That's not the logic here. The logic here, it opposes the change. So, I'll say it again. You can imagine 10 coming out, and the bar moves in, it's dropping down to 8 from the primary. Therefore, a current will be set up in the secondary to make up for that loss, so they've got to have 2 coming out. All right, so coming out, then this is where we have to go back to the previous chapters. We have that right-hand rule number 2, where if we have a loop, we put our currents in the direction of the current and our thumb in the direction of the field. Now, we don't know the direction of the current for this problem. That's what we're trying to find out. But what we have concluded from Lenz's law is that the current needs to be set up in such a way that the flux is coming out. The field is coming out. So that's why I'm going to take my right hand and point my thumb up. And then as I look at my fingers, I will see my fingers then are in a counterclockwise direction. And so there's the answer. According to Lenz's law, which opposes the change, the current is going to be set up in a counterclockwise direction, making flux come out, making up for the loss of flux in the primary because it's moving to the left. And I know that's a lot to take in. So let's try B here. Now, B has a little ring, and they're trying to show 3 dimensions. See if I can make a ring. I've got my little prompt here. Let me just kind of do this wire here. Okay, so this will be my ring. And it's probably not a good example of a ring because I've got multiple loops here. But ignore that for a moment. I think what they're trying to show here, and here's where some debate comes in, is this ring is clearly moving to the right. And it's clearly in a field that's pointing out. Okay. The question, though, is this ring kind of tilted so some flux comes through it, or is it completely flat and they've only drawn it kind of tilted so you can see that? And I'm not 100% sure, so I'll do both answers. I think, though, if I were to guess, I think they're trying to say it is tilted just a little bit so some flux comes out, but not as much as if it was fully this way. So I'll do that first. I'll say let's go with the idea that this ring is then tilted a little bit this way. And so there is some flux coming out, and in this picture it looks like 3. So I'll just say 3 out. And then this ring is moving to the right. And as it moves to the right, you can see that it decreases. It goes down to 2 out, and if it moves a little bit more, it would be 1 out. And so the flux we're getting from the primary is decreasing. So the current would be set up in such a way, making another field, what I call the secondary, to make up for that loss, because it opposes the change. So we must be making some flux that comes out. And just like we did in A, this is a ring, so grabbing my right hand, pointing my thumb outward for the flux, looking at my fingers, I'm going to get, again, this counterclockwise direction. And I guess I didn't put here counterclockwise. Now, if they meant for this ring to be completely flat, and they only drew it so you can tell that they're trying to lie it flat. So in other words, you're kind of looking up at an angle, but the flux lines go straight perpendicular to it. Let's see, I got a little pointer that works pretty good here. It's old broken pencils here. So if they're trying to say the flux is pointing up like this, and they're trying to say the ring is completely in the same plane as the lines, and that our view has a little angle to it so we can kind of see through that, then I would say, well, there is no flux going through this ring, and so when it moves to the right, it doesn't change because it just goes from nothing to nothing. So there is no change and therefore no current. So it's a little difficult exactly to know what the author is trying to do. But while I was babbling on, I kind of looked up the solution guide, and they show a counterclockwise. So at least the answer from the author's solution guide does seem to imply that there's a little tilt to it, a little bit of flux, and then it comes out. All right, again, hopefully you're going to see that same logic in these other 4. All right, so let's come over here. Here's the ring. And it looks like they have it moving to the left. And it looks like it's partly in and partly out. But I would have, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll call it 10 out. And as it moves along, or at least until it gets to this edge here, there is not a loss in flux. Oh, I'm sorry. I was looking at my own arrow. Sorry, my bad. It's moving in. Okay. So definitely then it's an increase in flux. So we have 10, and as we get further in, it's going to kind of fill up the space with flux. And so the 10 is going to become an 11 or perhaps a 12. But again, keep in mind that Lenz's law says it opposes the change. So since the flux is increasing, the secondary wants, instead of out, wants to be in by 1 or in by 2. Because by the time you put in, the increase of the primary, so the primary goes up from 10 to 12, then the induced current is set up to go inward. By the time you have 12 coming out, and then the secondary 2 going in, we're back to the original 10. And that, again, is what I'm trying to emphasize. Lenz's law says it doesn't oppose the flux, it opposes the change. It wants to set up a current and a secondary field that keeps the flux back the way it is. So if the primary increases, the secondary would decrease it. Or as in this one, if the primary is decreasing, the secondary would be increasing. Okay? It opposes the change. All right, now the same logic as before, going back to a chapter. If we have current in a ring, we can represent the direction of the current with our fingers, and we can represent the direction of the field or the flux with our thumb. And so we've just argued that we want our flux to be in. That is, with our right hand, our thumb pointing inward. And then looking at our fingers, we would see that it is going in a clockwise direction. And so C should be, let's see, did I do that right? A, B, C. And so C should be clockwise. And like I said, I called up the solutions, and the solutions say counterclockwise. Makes me think I did something wrong, but I don't see it. So this is a decrease in flux, and then this would be an increase in flux. So we want to go in. Yeah, I maybe that's why I got the question from somebody. They're like, wait a minute. Shouldn't this be clockwise? That's weird. I think that's a typo. Let's try this one too. Because now that I look at the answer, all the answers to the author say counterclockwise, 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 counterclockwise. And no, that can't be right. All right, so I think something went wrong in whoever was making the solution guide, and counterclockwise, 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 yeah, they got counterclockwise for every one. I think it's just a copy and paste typo there or something there. All right, so counterclockwise, counterclockwise, clockwise. And this one kind of looks the same thing, that you can see as it goes across, it's the opposite of this. It's an increase in flux. Let's just run through it, but I'm pretty sure this one should be clockwise also, because it's going to be a lot like this one and the opposite of that one. And so again, it opposes the change. So looking at this loop right here, as the bar goes out, there's more and more flux coming out. That means the secondary needs to be set up for the flux to go in. And so putting my thumb in, this would be a clockwise direction. Interesting. And I guess I'll just have to apologize for the author here. That's unfortunate. Maybe I should drop this one because that can just lead to more confusion. But I'm going to finish this video and send it to you. So watch this. Here again, they directly say the field is increasing. And so we don't have movement here, but we do have an increasing field. And because it's increasing, the current is going to be set up in such a way that the flux opposes that change, which would be a inward to counterbalance it. And so putting my fingers inward, this right here should be a clockwise. And then right here is kind of the decreasing effect again. So it's going to be the opposite of this. So I'm sure this is a counterclockwise direction. But again, I have a bunch coming out. As the field decreases, that's less coming up. To make up for that, the secondary wants to come out. So I'm going to put my thumb out, and that's going to be a counterclockwise direction. In fact, I like the way the author has these 6, because if you look at them, 3 of them are an increasing flux. There's an increasing flux here. There's an increasing flux here. And there's an increasing flux here. And he's given you the 3 possibilities of increasing the flux. One of them right here is just the strength of the field gets bigger. Another one right here, he says the ring itself actually moves into the field, making more flux. Or this one here, where the ring actually gets bigger. The only 4th possibility is that you could change the tilt angle between the field and the ring, kind of like we talked about here, and he doesn't do that one. But it's almost complete. He does the 3 common ways of increasing the flux by either increasing the field, increasing the area of the ring, or increasing how much of the ring is being emerged in the field. And then you have exactly the reverse of that. Maybe I'll circle those in blue, but you've got a decrease here, and this is because the ring or the loop is getting smaller. Here, you got a decrease in flux here because it's exiting, so it's kind of the opposite of this one, and it's like this is the opposite. And then here, we've got a decrease because the field is decreasing. But all the ones that are decreasing should be in a counterclockwise direction, and all the ones that are increasing should be in a clockwise direction. All right, again, let me apologize for the author, but now I see why people are asking this question when if they're comparing it to the solution. So the author just didn't do a good job here. But I still like the problem. I just think I should probably drop it because the solution guide makes it misleading. But great questions. All right, take care.